All right, so share screen. So here's the code we were working on last time. Um, so if we look at, oh, I was about to say if we look at the client, but the client doesn't seem to be there. There we go. So what we did last time was we got insert taken care of and we got print taken care of. So let's start with just a simple little one. Let's do size. Okay, and of course we could keep a separate size data member, but we've chosen not to do that. So we're going to actually have to write some code that looks for the size. So here we go. We're going to have int binary tree : size, no parameters, and it's just going to say return size args, sending it the root as an argument. Okay, so that means we're going to have a size args function. Let's go back to our header file and static int size args, const. Everyone okay so far?
Yeah.
So now we need a size args. All right, so base case.
It's a leaf.
Base case is a leaf. That would be okay, but we can. I'm not sure if you'll remember this, but when we talk about recursion, we talk about always trying to find the absolute simplest base case we can, and we can do simpler than root is a leaf. If root was a leaf, that would mean the size was 1, right? So we'd return 1.
Empty then?
But right, if it's just empty. So if root equals null pointer, return 0. Else, return size of the left subtree plus the size of the right subtree plus 1. How does that sound?
Good to me.
Any questions about that? Okay, so a lot of this should be looking pretty familiar by now. We've seen recursion enough, and this is actually fairly similar to print. The main difference being that print is a void function. So when root is equal to null pointer, we just do nothing. But anyway, let's give it a try. So return type void or something. Int.
Something declared as size type or something?
Int. What happened? Oh, yeah, okay, you're right. I guess that's actually preferable. I'll go with that. I forgot we were doing that. So yeah, both of them should just be size type. I thought I forgot to save something. Unknown names. Oh boy. Haha.
Let's just make it int. Go full circle.
Nah, we're okay. We'll make this one.
Yes, just a scoping problem, of course.
There we go. All right, so let's put some numbers in our tree. Always like to try to, ooh, 2 5s, to make things a little bit random when it's a binary search tree, because if I do them just 1, 2, 3, 4, 5, 6, then they all go in a straight line, right? All right, that's good enough. So there's our binary search tree. There are 7 items, is showing that our size function seems to be working, okay? Any questions about size? All right, here's what we're gonna do. I realized in the middle of that my notes are in a different location than I am. So I'm just gonna take like 2 or 3 minutes here and get those because the probability that things will go smoothly will increase. But I'm gonna do this. All right, give me like just a second here to run to the printer. All right, feeling better already. So, you guys still with me?
Yep.
Okay. Let's go look at our client again, see what's next. Looks like the next thing we need to do is define a find function. So I will uncomment that section of the code. And let's go uncomment find. looks like we're actually almost done with this. So that's good. Might have kind of a short class today. All right, I'm just going to predict in advance that we're going to need a, by the way, I'm actually returning int this time and not size type, because what I'm going to be returning is actually what I find in the tree, right? It's not related to the size of the tree. Find logs. Okay. All right, so int binary tree corn find, and the parameters of target. Right, so the way I have it set up here is I'm going to also have a second parameter called found that just gets set to false if the thing we are looking for was not found. And so all we're going to do here is we're going to call return find odds target found. Try that again. That's why I have my notes. Root target found. Any questions about this? Why we had to put root in there?
No questions.
Okay. So now we need find odds. This should be const. Okay, so base case. Going to be actually a couple of base cases here. One base case will be tree is empty. What happens in that case?
Oh, we return false, I believe, but we also need to use the binary equals operator, I think.
Oh yeah, right. Okay,
or,
so
yeah.
So we're going to set the parameter found to false, right? So if the root is null pointer, that means that the thing we're looking for isn't there, right? So we're going to set found to false. We have to return something just because that's a C++ rule, right? If we have an int function, we have to return something. I could just say return 0. Just to demonstrate, I guess. I mean, we've seen this, I think, 5 or 6 times now, so it shouldn't be anything new, but just to demonstrate that we could change into something else and things will still work. We could make this into a templated class if we wanted to, and things would still work. I'm going to write it like that. That just means return whatever the default value for int is. Okay, so that's one base case. What's the other base case? How about we found what we're looking for, right? So else if root arrow data is equal to target, then found is true, and we return root arrow data. Okay. So I think we've had this conversation before, but I'll just repeat myself, I guess. It may seem a little odd that all we're doing here is just returning the data that it was we were looking for. What you have to keep in mind is that this is a super simplified version, right, of a binary search tree. Typically, what's going to happen is you're going to have some sort of a record in there or some sort of a complex object that's being stored in there. And we just looked for it based on some sort of an ID or a key. And what we're going to be returning then will be the entire node with all the data in it. So we will get to see that actually. But for now, we're just going to say return whatever the data was we found.
Right.
Okay, so those are our base cases. Now we just have to handle the cases of the thing we're looking for is in the left subtree or the thing we're looking for is in the right subtree. So else if the target is less than root arrow data, then we're going to return find odds root arrow left target else return find odds root arrow right target. Okay. I went to all the trouble of getting my notes and now I'm not even looking at them, but that looks right. Any questions about that? Anyone think that's not going to work? Anyone want
I wanted to ask if find was declared const, because that might cause us a compilation error. But the logic looks like
to? That's a great question. You're right. The find function should be const, right? So should size, now that I think about it. There's some problems here with my notes I need to work on. Size should be const, right? Print should be const. Wow.
it's one of those things that I'm not very good at, so I've been trying to work on it.
Print size font. We're not changing the binary search string. What about print ogs and size ogs and find ogs? Should those be const?
I don't see why not necessarily, but.
So here's the deal. Static function, no calling object, right?
Oh yeah, of course they can't be. Oops.
Right. That makes sense to everyone. So because these are static, they're not associated with any particular calling object. So that means that it does not make sense to make them const. That would give you a compiler error. All right, let's check this out. See, I mean, we made enough changes. There's got to be at least one compiler error, right? Yep. Found. I forgot to. This is in the client. Oh, just need to uncomment that. Okay. Out of line definition of find ogs does not match. Okay. So find ogs.
3 arguments.
Oh, duh. Right.
Yeah.
There we go. Okay, so let's put some numbers in. There's our numbers. We have 8 of them. Enter a number to find. Wonder what no. So what? This is a good question, actually. What number is at the root right now? So it turns out that if we are just inserting things into the tree, remember, whenever we insert something into the tree, we put it at a leaf, right? So a corollary to that is that the first number that we inserted is going to be at the root. So the 6 is at the root. And the reason I thought of asking that is I thought, well, let's try let's try finding what is at the root first. So I'll try finding 6. That seems to work. So 2, the last thing we inserted, so that's going to be a leaf. So let's try 2. And, I guess we might as well just try as many as we want. Try something that's not in there. Looks like we're in good shape. Okay. Any questions about find? All right. Let's move on to whatever's next in the client. And what is next in the client is we're going to write a function named del. Can't use delete, obviously, because that is an operator in C++. Okay, so we're going to write a function named del. There's the prototype. I need an aux function just like all the others. It's not const this time, though. So this is like insert, right? Because we may change the tree, or we will, well, unless we don't find it, we're going to change the tree. So I need to pass it by reference. Okay, so hopefully I got everything right this time and I won't have to fix compiler errors, but I wouldn't place any bets. Okay, so we need a del function. Void binary tree : del that just takes a target and found, and that's just going to call del aux with the root and the target and found. Okay, and then we'll want our aux function. Okay, deleting from a binary search tree is really, really interesting. I actually personally have a recollection of applying for a job the summer after my senior year in college and being asked to explain how to delete something from a binary search tree and not getting the answer right and also not getting the job. I think it's one of those questions that tend to show up in interviews a lot, not to mention exams. So anyway, make sure you get this. Let's dive in, but then I think we're probably going to end up wanting to go look at the diagram of the tree at some point. But so there'll be a couple of base cases again, right? So might as well shoot here and look at my notes if I have them. If the tree is empty, then we just set found to false and we're done, right? Now, in this case, the deleting of the node is the hardest part. So I'm getting, and that's a base case, right? One of the base cases is going to be, we found what it is we want to delete, but then there's still going to be quite a bit of work to do. So I'm going to try to take care of the easy stuff first. So I'm going to do the recursive calls first this time. So if target is less than root arrow data, then I'm just going to call del augs with root arrow left target found. Oops, that should be also. Else if target is greater than root arrow data, del augs root arrow right. Okay, so all that's left now is we have to write the code that's going to actually delete the node from the tree. Okay, so it turns out, let's look at this. I'm going to break this down into a couple of cases. Let's say that I'm deleting the 50. Trying to make this so that we can see the code and this at the same time, but that works. So if I'm trying to delete the 50, the left, so that means that root is going to be this arrow here pointing from the 60, right? Everyone okay with that? If root is this arrow here that's pointing from the 60, and I'm trying to delete the 50, because there's no left subtree here, I can simply make root point down to root's right subtree. Does that make sense? So basically, I just need to take this arrow and point it down here. And that gets rid of my 50. Okay, so what I'm saying is if root arrow left is null pointer, then I can do that. And just to point out, this also works if root is a leaf, right? So if let's say I'm trying to delete the 65. So the rule still works. If root arrow left is null pointer, which it is, set root equal to root arrow right, which is also null pointer, but I don't have to make a special case out of it, right? So here's the code to translate everything I just said. If root arrow left is equal to null pointer, then I'm just going to make root point to root arrow right. And I'm done with that case. Except for the memory management part. Well, actually a couple other details, but that's the basic idea, right? That everyone's, any questions about why that works? If I'm trying to delete the 50, that makes this arrow here pointing from the 60 to the 50, that's root. And so root arrow left is null pointer. So I'm just going to make root point to root arrow right. Okay. we also need to make sure that we deallocate that node, right? So I'm going to have to end up saying, set a temp pointer equal to the root, which is the 50. And then after I have moved root, then I can delete temp pointer. And then I also have to say found. Okay. So that takes care of the case where the left root, where root's left subtree is empty. So the only thing we have left to do now is how do we delete a node if it has a left and a right.
What if its right subtree is empty? We can do that.
Yeah, so if its right subtree was empty, so that would be like if root was this arrow pointing from the 60 to the 70, then we could have another case that says if root arrow right is empty, just make root point to root arrow left, right? However, it's going to turn out that case is going to be subsumed by what we're about to do anyway. So
okay.
we're gonna let that go for now. All right. So, but let's talk about if we are trying to delete a node that has two non-empty subtrees. So let's say we're going to try to delete the 60. Here's what we're going to do. We are going to find the largest item in root's left subtree, and we are going to replace the 60 with that node. Okay, so let me say that again and make sure that it makes sense why that's going to work, right? We know that everything to the left of the 60 is less than the 60. So if we find the largest item in 60's left subtree and put it here where the 60 is, then that's we're still going to have a valid binary search tree, and we're going to be done with the 60. Okay, and then we just have to make sure that we deallocate that. And so the largest item in 60's left subtree, we can always find that by just following the pointers down to the right. Right, the largest item in a tree is always going to be just keep going to the right as far as you can. Right, take the whole tree, the largest item in the whole tree, start at the root, go down to the right, 70. The largest item in this left subtree over here, start at the 20, go down to the right, 35. Okay, so the way to find the largest item in a tree is to just follow the pointers down to the right until you get to a null pointer. Or until you get to a node that does not have a right child. All right, so that took a lot of words. It's not as complicated as the number of words that it took to say it. Basically, let's just take a different example. Let's say that we are deleting the 40, okay? The way we're gonna delete the 40 is we are gonna find the largest item in 40's left subtree and swap it up to where the 40 is. So we're gonna put the 35 up here. That's gonna maintain our valid binary search tree, and it's gonna get rid of the 40, okay? Anybody want me to talk about that more before I turn it into code? Because the code's not gonna make any sense if the description didn't make any sense.
Makes sense.
Okay. All right, so let's do that. Else, Okay, notice how we've kind of gradually narrowed it down here. So now we know that at this point we have found what it is we want to delete. Root is pointing to the node we want to delete. And that node has a right child, or left child, I mean, right? Then, yeah, that node has a left child. So here's what we're going to do. I'm going to use a little decomposition here. I'm actually going to write a function called remove max. And what that function does is it's going to remove the largest node in this tree, but it's going to return the contents, the data in that node, in this second argument here. That makes sense? So if I call remove max on the tree whose root is 40, it's going to remove this 70 from the tree and set max equal to that 70. Right? So then what I can do at that point is I can just say root arrow data gets max, because that was the largest item in root's left subtree, and then found gets true. Okay, we still have to write the remove max function. Any questions about this code now? Again, remove max is just going to be a function that takes two parameters. It's going to find the largest item in its first argument, deallocate that item, but set max equal to the data that was stored in that node. Okay, so let's work on that. Void I'm thinking remove max should be a member function, right? My notes don't have it as a member function. No, it shouldn't. Oh no, so it's going to be like an OGS function. But I mean,
It
not
doesn't need
OGS.
to be member. You pass it root node, right?
Well, I mean, I don't really want it to be a global function. What I want it to be is a static function.
Right.
But that's still a member function. So I think
Oh, I see. Yes, yes, of course.
I might need to work on my notes a little bit here. So binary tree, colon, remove max. I don't need that because it's already. Max. Okay, so I'm going to write this recursively. I'm going to say, so the recursive case is just going to be if there's a right subchild, if there's a right child, call remove max on that right child. And that's how we're going to move down the chain to the right. But the base case, if root arrow right equals null pointer, right? If we have gone down to the right as far as we can, then, so the easy part is I'm going to set max equal to root arrow data. And then I need to, so let's say that root is this arrow here pointing at the 70. I got to a point where root arrow right is null pointer. So what do I need to do to remove this node? Well, I'm going to make this, oops, I'm going to make root point to, I'm going to make root point to root arrow left, right? That's how I get rid of, that's how I remove this node from the tree. Okay, so again, the remove max function is doing two things. It's setting the max equal to the data in the largest node. but it also needs to actually remove that largest node from the tree. The way we're going to remove that largest node from the tree is we're going to say root gets root arrow left. Okay, so we're done with the base case, except for a couple details, but that conceptually we're done, right? The details are we need to actually deallocate that node, and we need to, that's it actually, we need to just deallocate that node. So before I move the root pointer down, I'm going to set, this will look a little familiar. Okay, so there's our base case. We've reached the end of the chain going down to the right. And so we remove that node from the tree. So for the 70s, a good example of that. Let's go with that. And then we have the recursive case, which is we're just going to call remove max with root arrow right. Okay. Let me just say that there's a lot going on there, but if it's not completely clear right now, I know that if you stare at this for a while, you can figure out what's going on with it. And if you can't, let me know, okay? You know, this is definitely up there in the top 10 of what you want to take away from this semester. So make sure you get this. Anybody want to formulate a question about any of this? Okay, I still think I need to add, just remove max, I think. I have it in here. I've got it down here. That was my little cheat area. All right, let's try this. I winged it on a few things here, so we'll see how this goes. Ooh, look at that. So, does that mean someone just left? I just had an interesting sound effect.
Yeah, someone left.
Okay. I don't remember there being 6 of us, but anyway, I'll take your word for that. Okay, so we're going to insert some numbers. What did I just do?
I believe it was Patricia, actually.
Oh, okay. I don't think I noticed that she was here. Let's try this again. So number 2 insert. Let's do 10, 15, 20, 7, 12, 4, 9, 19. Okay, so we've got some numbers in there. I'm not going to test find again. We already tested find. So a number to delete. Let's see if we delete the node successfully. So I'm going to type 10. Okay, be really interesting to draw out pictures of what's actually happening here, because it's really interesting that this output that we have here actually tells us absolutely nothing about what the tree actually looks like, right? When I delete the 10, what does that mean? And we probably have to go back and look at the code. But if I'm deleting the root, then our code says, because neither subtree is empty, I'm going to find the largest item less than the root and put it at the root. So now 10 was at the root before. Now, if I were to draw a picture of this tree, 9 would be at the root, right? Because it's the largest number in 10's left subtree. Anyway, just interesting to think about. And of course, we could write some code to actually draw a picture of the binary search tree if we really wanted to. Okay, so I'm gonna just start deleting a few things and make sure it seems like everything's working. 14 is not on the list, 15 is deleted, 4, 7, 12, 19, and now I have an empty tree. So it looks like we got it. All right. That's all I have for the binary search tree example. They're basically what you're going to be doing in the assignment is adding a couple other functions to this, and also adding the big 3 to this. Because actually in my tree client, I don't remember if I give you this, so I probably shouldn't even show you it, because you should be able to come up with your own code to test for the big 3. But this code here, basically the purpose of it is to test the big 3. And if I run it right now, I need to recompile, but okay. 10, 15, 12, 9, 3, 8, 4, 29. I'm not going to find anything. I'm not going to delete anything. And so now look at what it says. It says list 2 should be a copy of list. Here it is. 3, 4, 8, 9, 10, 12, 15, 29. That looks correct. 3, 4, 8, 9, 10, 12, 15, 29. After deleting 3 from list 2 is now that, which is correct. But list should be unchanged. Oops, the 3 also got deleted from list, right? So that tells us that there's something wrong with either our copy constructor or our assignment operator. And then the same thing will happen again. So that's going to be part of what you're going to do in your assignment. All right, any questions about anything before we go?
Yeah, for issues, would you say it's better to email you or comment on that discussion post, do you think?
If it doesn't involve sharing any of your code, then it's better to ask in the discussion.
Gotcha, thanks.
Right. Cool. All right. Well, good luck with this. Hopefully it'll go smoothly, and let me know if you get stuck. And well, I see you on Thursday. I believe that I will see you on Thursday. Yeah.
Thanks, Professor. Take it easy.
All right. See you.
Thanks.
Oh, just saw there's a billion chat messages.